So with our first data analysis part 1 review, here are the answers already listed on here. I'll go through them slowly if I can. So they collect data about dogs they house, and which of these is categorical. I think the easiest question on the page. We know that cost, weight, age, number of days housed, those are numbers, those are numerical values. They can be manipulated. So the answer obviously is breed. So the answer to the first one is breed. That is a category. So the second question, still using the same 5 choices, which of those variables above about German Shepherds is most likely to be described by a normal model? And that is going to be weight. As I've discussed before, weight of any creature, pretty much, people, dogs, cats, animals, whatever animal we're dealing with, is going to most likely be approximately normal. Now, it doesn't say it is normal. Okay, it can be described by a normal model. That means it just has the normal model shape, but it's not specifically, just like the ones you created that you found online that had the histograms and the various other graphs that you then drew, had the curve overlaid. Those are normal models describing a data set. So that's going to be weight of the dogs. And so they kept record for the past 20 years. If they want to show a trend in the number of dogs they have housed, what kind of plot should they make? And the best type for that is a time plot to show the increases and decreases over time. Okay, and that's strictly what a time plot is. It's something, especially something 20 years in length. You could almost make either talk about a histogram or a box plot. Box plot wouldn't be that good. Histogram would be okay. Time plot's best. These two are for categorical data, and this is not categorical data. This is the amount of time each dog stayed. So these are bad answers. Okay, a box plot's really not a great answer because we want to show trends. To show trends is best as a time plot. And that's pretty much what almost this is, this OJIV, for the veterinary bills. The vet bills for the dogs are summarized in the OJIV shown. Estimate the IQR of these expenses. So if we come right here, we know that IQR, at least I hope we know that, is Q3 minus Q1. It's Q3 minus Q1. Well, Q3 is the third quartile, and it's 75% of our data. 75%. The first quartile, Q1, is the first quartile or the first quarter or the first 25%. So Q1 quartile 25%. So I come here to this and I'm going to find these two numbers. I can find Q1 first. It's the 25%. So if we go and look here, this line represents 20. This line represents 30. Halfway in between those two is this point right here. Okay, halfway between those two is that point right there. And if I line that vertically with the horizontal axis, that is about $75. And so we do the same thing with Q3. Q3 is 75%. So here's 60, and there's 80. That means this line is 70. We follow it across. Here is 70. There's 80. About halfway up is 75. And again, I'll drop a vertical line here. And that amount looks to be halfway between 150 and 200, which is $175. And so we've set it. It's Q3 minus Q1. So that's $175 minus $75. And that is approximately $100. And that's the reason why the answer is C. C? C. Bueno. All right, number 5 is last weekend, police ticketed 18 men whose mean speed was 72 miles an hour. So we had 18 people, 18 guys, whose average speed was 72 miles per hour. So that means they added up all 18 of their speeds, divided it by 18, and got this. So we need to take 18 times 72. We need that grand total because we're finding the averages here. So 18 times 72 is 1,296. So this sum total, the total speed of the guys was 1,296. So we had 30 women. This is men, this is women. Their average speed was 64 miles per hour. Must have been on a 60 mile an hour or a 55 mile an hour. That tells you how old this is. So we have 30 times 64 because we need their total. Because to find the average, we need the total number of people, which is 48, and the total speed. And so we multiply 30 times 64. Excuse me. I get 1,920. So now I'm adding these two. Okay, we're going to add these two. And I get 3,216. I divide that by 48. So we take 3,216. 3216 divided by 48 is 67. So the average speed of all the males combined with all the females is 67 miles an hour. It can be determined. Most people don't think it can. Now, the main mistake is people do is they take 64 plus 72 and divide by 2, which is 68. Close, but no cigar. I'm not going to give you credit for that one. Not going to give you credit for that one. You have to find the sum of the men's, which was 1296, the sum of the women's, which was 1920, add them, and divide that sum by the number of people, which was 48. So then for question 6, it says which of the is true of the data shown in the histogram. So we have this histogram. Okay, this is definitely not approximately symmetric. And as I look at this, if I take and just kind of draw a curve describing this, the curve kind of looks like this. And this is where I talked in class today, or not today for those who watch this in the future, but this shape, if you can see it, is kind of like the dinosaur. This is the top, this is the head, this is the biggest part of the body, and the tail pulls away. So this, we call this skewed to the left. Okay, this is my left, it's my left hand, the L, it's skewed to the left. This says the distribution is skewed to the right, so that is not a true statement. The next one says the mean is probably smaller than the median. Okay, this is an idea and a concept you need to put into your brain. If we're talking about a normal distribution, we want the mean and the standard deviation. But when a distribution is skewed, we want the median and the IQR, always and forever. Always and forever. If we have that, we have it set up that way. Normal distribution means standard deviation. Skewed, when we're talking about the median and the IQR, I would say that the median is probably somewhere in this general area, contained somewhere in those two bins, because these two combined are almost probably half of the data, whatever this data is. And so we use 3 is an acceptable part. We use the median and the IQR to describe the distribution since it is skewed. Now, it is called skewed because of these low numbers way out here, almost like outliers. This tail over here pulls the mean to the left. Our median is somewhere in here, but my mean for this data set will be over here because of these low numbers pulling it that direction. So these two are both correct answers. The mean is probably smaller than the median, and we would use the median and IQR to summarize the data, and that is answer D, 2 and 3. 1 is not. This is skewed left, not skewed right. Please get that into your brain. Follow the tail. The tail tells me the direction. Tail tells me the direction. This tail tells me to the left. Okay, so now let's answer these two. A best estimate, sorry, let me straighten up my life here. So we have the best estimate of the standard deviation of the men's weights displayed on the dot plot. Okay, there's 93 numbers here. So we could look at, okay, we want to find the distribution of this. There's various ways of finding this. So we're trying to determine the best estimate of the standard deviation of the men's weights displayed in the dot plots. So if we look at it this way, if we think, okay, one standard deviation from the mean, which the mean looks to be approximately, or the median and the mean both look to be approximately right there. It's somewhere in that general area. So knowing that, we know we could count the dots. There are 93 dots here. There are 93 dots on the dot plot. And so, excuse me, we want the middle part of our graph. We want the middle percents. Well, we know that 68% is here. Agreed? 68% is one standard deviation above and below. So if I click on here and I go 93 times 0.68, I get about 63 dots. Okay, so that's a difference of 30. So I want to go in 15 dots on each one. So if I go in 2, 4, 6, 8, 10, 12, 14, 15, right about here, 2, 4, 6, 8, 10, 12, 14, 15, right about here. So I'm about 140. This is 140, a bunch of 140s, up to 180. This is 185. Okay, so if I go 185 minus 140, that's 45 divided by 2 equals, that's 22 and a half. So my standard deviation is about 22 and a half, and this is the closest one to it. So it's 25. I found 68% of 93. That's 185. That's counted 15 on each side. Okay, that's 63. So I counted the difference of 30, counted in 15, guesstimated about where my first standard deviation would be, 68% of the data here. And so that allowed me then to determine 22 and a half, and the closest number to that is 25. Okay, question 8. Let's get on with this. If we want to discuss any gaps and clusters in the data set, which of the following should not be chosen to display? Okay, histogram looks like this. Okay, and if we have a gap, we might have a gap in there that looks like that. So we can see gaps in a histogram. A stem plot looks like this. We have our stem and leaf. This means 10, 13, 14, 25, 26. Okay, we see there's a gap there. We see each on a stem and leaf plot, we see every individual piece of data. So that wouldn't show, that's good about showing gaps and clusters. Histogram is. Dot plots, there you go. There's my gaps, there's my clusters. And so a box plot shows us nothing about gaps because it's continuous. Okay, question 9. So the question is asked, suppose a normal model or statement is made. Suppose a normal model describes the number of pages printer ink cartridges last. If we keep track of printed pages for the 47 printers at a company's office, which must be true. Okay, here we go. There's a phrase here that's horrible. We'll start with the first one. The page counts for those ink cartridges will be normally distributed. We don't know that. Will be is a ugly sign. We don't know that. The histogram for those page counts will be symmetric. We don't know that. We don't know that they will be. Both of this might be. This is roughly symmetric because remember, we know it won't be symmetric. 95% of those page counts will be within 2 standard deviations of the mean. We don't know that. We can't say that for certain. It said it describes it. It didn't say it was. It didn't say it's an absolute miracle that occurred. So the answer on that one is none, because none of those describe that. Not a single one of them. Pause that and re-listen to what I said if you need to. Okay, so here we go. We have a normal model that describes fuel economy, miles per gallon for automobiles, and a Saturn has a standardized z-score of 2.2. So in other words, we have a normal model drawn, and here is our mean. Our mean is 0. This is the average miles per gallon. Well, there's 1 standard deviation, there's 2 standard deviation, and right here is where Saturn is, at 2.2 standard deviations above the mean. That's their z-score. What does that mean? Sorry, no pun. This means that the Saturn gets 2.2 miles per gallon? Well, obviously not. This is the average miles per gallon, which is some number. You can just make it up if you need to. Gets 2.2 times the gas mileage of the average car. Well, we don't know exactly what this median number is, this mean, and we definitely don't know what our standard deviation is. So it's not that. It doesn't get 2.2 more miles per gallon for the average car. No, it's 2.2 standard deviations above. It's a lot larger. As a matter of fact, folks, it's outside 2 standard deviations. That's unusual. We know that. That's unusual. It means it's a lot more than that. Has a standard deviation? No, it doesn't have a standard deviation of 2.2 miles per gallon. Z-scores never have a unit. Z-scores never have a unit. Z-scores never have a unit. And so it must be E. This means that Saturns achieve fuel economy that is 2.2 standard deviations better than the average car. Here's my average car. Here's the z-score for Saturns. Yeah, it's 2.2 standard deviations above that. So there's my 10 questions for the review. Feel free to rewind and listen to again, and soon I will post the free response questions. I hope you have a great rest of the day.